lesson, we are going to learn about properties of gases and how we can measure those properties of gases. So we're going to start with just that. We are going to start with talking about the measurable properties of gases that we can study. So measurable properties of gases include gases are easily compressible or easily compressed, and especially they are easily compressed when they are cooled. So for example, if you were to have a propane gas tank, the kind that typically fits onto an RV camper or in a propane gas grill, that is compressed gas. In fact, it's compressed so much that it's liquefied in there. When you toss that propane tank around, you can hear the liquid sloshing inside. But when you open up the valve, the gas comes out. So it is easily compressed when it's cooled, and that's how they have to get it into the compressed or the liquid form, is they have to cool it. But they are easily expandable too. Okay, easily, I guess that sort of goes along with if they're easily compressed, they're likely to be easily expandable. This is especially true when they are heated. So what we see here is that there is a definite relationship between temperature of a gas and its volume. Gases have a low density. They're usually measured in grams per liter, and so that just means that for 1 liter of gas, this would be a very small mass. That also explains, or maybe you can imagine that it explains, why gases tend to rise. Certain gases tend to rise, especially compared to the liquid that they might have come from. Another property of gases that can be measured is that they exert pressure. And we can measure that pressure, and we'll be talking about how we measure that in just a moment. But the idea here is that these are all observable and measurable properties of gases. And what we are going to be doing in this unit is we are going to attempt to explain this behavior with respect to what the particles of the gas are doing. So we can say that the behavior of gases can be explained by what is called the kinetic molecular theory. And we are going to abbreviate that as KMT because it's just a little bit of a handful to say. So KMT is the kinetic molecular theory, and which attempts to describe the motion, the collisions, and something that is called the it's abbreviated as IMAF, which are intermolecular attractive forces. And we'll be talking about those in the next unit. But kinetic molecular theory attempts to explain the behavior of gases based on the motion, the collisions, and the intermolecular attractive forces of the particles of the gas. So this is what gets a little tricky, is because you can't see these particles, and you have to sort of imagine what they're doing, and understanding that the way that the particles behave will translate to the measurable and observable properties that we can see of gases. So we're going to take a look at these, starting first, just sort of understanding gas, liquids, and solids. Right, here's a picture of what the particles are doing in those 3 phases. Now, mind you, this unit, we are talking exclusively about gases, but it is helpful to understand particle arrangement between the 3 phases of matter. So what do we know about particle arrangement in a gas? Well, first of all, they are far apart, and the particles will flow. Right, so they're kind of like a fluid They will easily move around, and their spacing is that they are far apart. And particles flow, and they're relative, well, I'll come back to that. The liquid phase, the particles are close together, but the particles will flow. And taking it one step further to talk about the solids, we are talking about particles that are close together, but this time the particles are in fixed position. So what happens here is as you go from a gas to a liquid to a solid, the relative kinetic energy of that substance decreases. So in the gas phase of a substance, those particles have relatively high kinetic energy of motion. As you have to cool a substance to get it to a liquid form, and what you are doing is you are removing kinetic energy. So this, by comparison, would have a medium kinetic energy. Cooling it yet again to become a solid, you would have low kinetic energy relative to that same substance in those other phases. Solids and liquids are not affected nearly as much by changes in pressure, temperature, or volume. And why is that? Well, it comes down to seeing what's going on with the particles, right? So if you look at gases, the particles are very far apart. And when we say they're very far apart, we're talking about with respect to the size of the particles themselves. The size of the particles are very, very, very small. And so the distances between them are enormous compared to the size of the particles. So the particles are very far apart to begin with, and solids and liquids, the particles are close together. Right, so if you're trying to compress a gas, you can, because there's lots of space in between them, and you can push them close together. But liquids and solids are already very close together, and so there's not much room for further compression. Right, so particles close together, they can't be compressed. And we can say that they're easily compressed. Gases are easily compressed. And it turns out that, here we're citing evidence of pressure. But pressure, temperature, and volume, certainly of a gas, are all very interrelated, and we're going to be exploring these ideas as we progress through the first part of this unit. Okay, we are going to, we're going to change this a little bit. This should say define the three quantities. We're not going to take a look at how they affect each other in this lesson. Pressure. So we're talking about pressure, temperature, and volume. These are all things that we can easily measure and observe about gases. So let's just talk. We have to kind of make sure we're all on the same page with understanding what these things are. Pressure is a result of simultaneous collisions of billions of rapidly moving particles of a gas on the walls or with the walls of the container. So as the particles are moving around in the container, when they hit the walls of the container, that force is considered pressure. How do we measure gas pressure? Well, there are different scales that we can use to measure. And in this class, we are going to be using most commonly something called millimeters of mercury. And this is actually the unit, mmHg, millimeters of mercury. And the mercury they're talking about is in a mercury barometer. Another scale that we use, which is, the abbreviation is ATM. And I know I didn't write that very clearly, ATM, which stands for atmospheres. And easiest way to think about this is that 1 atmosphere is the pressure exerted by the atmosphere if you were standing at sea level. So you're standing at the beach, you have exactly 1 atmosphere above you, and the weight of that atmosphere on you is equivalent to 1 atmosphere. A third scale that you'll see used in this class abbreviation is kPa, which stands for kilopascals. And kilopascals are actually, pascals are the official international unit for measuring pressure, so that's why we'll be addressing it here. Atmospheres, you're going to see, is the easiest one, it's the easiest scale to manipulate mathematically, and millimeters of mercury it's sort of an archaic, originally when pressure was first being measured, that was the original way that scientists were measuring pressure. So converting between these units is going to be a useful skill. We're going to use our dimensional analysis technique, and that means you need equalities. You need equivalent quantities. And what we're going to do is I'm going to tell you that standard pressure, just for consistency's sake across the scientific community, is equal to 760 millimeters of mercury. And that millimeters of mercury pressure unit is equivalent to 1.000 atmospheres, and that is equivalent to 101.3 kilopascals. So any of these three units can be used to help you convert between pressure units. So for example, a gas is exerting a pressure of 151.4 kilopascals. What is this pressure in millimeters of mercury? So this is our given. This is what we want to solve for. And using our dimensional analysis strategy, we always start with the number given to us, 151.4 kilopascals. We set up a bracket, and immediately I want to cancel out kilopascals. So that'll go in the denominator. And I want to convert this to millimeters of mercury, so that'll go in the numerator. Then I just need to know these equivalents, and 760 millimeters of mercury is equal to 101.3 kilopascals. We won't need this for this conversion. So 760 goes with the millimeters of mercury, and 101.3 goes with the kilopascals. And kilopascals are going to cancel, and then it's just a matter of getting your calculator out, and let's see what we get. So 151.4 times 760 divided by 101.3, and it looks like we're going to maintain four significant figures, and it looks like that would be 1136. So that is 1136 millimeters of mercury. So 151.4 kilopascals is equal to 1,136 millimeters of mercury. All right, let's take a look at temperature. We've learned a little bit about pressure and how it's measured. Let's take a look at temperature, something that maybe you're a little more familiar with, but we are going to look at it through the lens of a chemist's eye, a scientist's eye. And so temperature is not a measure of heat. It is actually a measure of the kinetic energy, which is the energy of motion, of the molecules or the atoms or whatever particle you are studying. So temperature is a measure of kinetic energy. And so to this end, the best scale to use for measuring temperature is going to be Kelvin. You are probably used to hearing temperatures in Fahrenheit. Maybe you've had a little practice with measuring temperatures in Celsius. But Kelvin is going to be the temperature unit that we are going to rely on in this unit. And that is because if you have 0 Kelvin temperature, then that means there is 0. I'm going to put a strike through this to recognize that this is a 0 and not the letter O. But 0 Kelvin is equal to 0 movement of molecules. So when we talk about 0 Kelvin, this is a special temperature known as absolute zero. And absolute zero means molecular motion stops. The universe cannot get to a temperature colder than absolute zero, at least not in the universe that we are participating in. And so what's great about this is because 0 Kelvin is 0 kinetic energy, we can now use Kelvin proportionally. And that's the important reason why we are using Kelvin. So for example, comparing 100 Kelvin, comparing that to 50 Kelvin, 100 Kelvin is 2 times the kinetic energy of 50 Kelvin. You can't do that for Celsius temperatures or for Fahrenheit temperatures because 0 Celsius does not mean 0 kinetic energy. 0 Fahrenheit does not mean 0 kinetic energy. So this is why Kelvin is a very useful scale for temperature. Since temperature is measuring kinetic energy, the Kelvin temperature is proportional. So just to talk about the commonly measured temperatures, let's just step back to that, right? So there's different scales that you are familiar with, right? There's something called Fahrenheit, which is spelled funny, Fahrenheit. There's Fahrenheit, that's the one that the US uses pretty predominantly. There's Celsius, which we have used in class, and you're probably used to seeing Celsius temperatures in a science class, and now there is Kelvin. And so to understand, right, so we have 3 thermometers. This first thermometer is degrees Fahrenheit. And so there's a couple of temperatures on here that we want to pay attention to, and I know the numbers don't point out really well. But based on water, water is an interesting phenomenon. The freezing point of water here in Fahrenheit is 32. And the boiling point of water here in Fahrenheit is 212. So the difference between the boiling point and the freezing point of water is 180 degrees Fahrenheit. That's not a very useful number mathematically, and so Celsius reconfigured this scale to be 0 degrees Celsius for the freezing point of water and 100 degrees. So the degrees Celsius scale between boiling point of water and freezing point of water, the scale here is 100 degrees. Okay. So this is 0 degrees. This is the freezing point. This is the boiling point of water. The Kelvin scale is really the Celsius scale, but the 0 point has been moved down to represent 0 kinetic energy. So the equivalent temperature for the freezing point of water in Kelvin is 273 Kelvin. Technically 273.15, but we're going to just round it to the nearest whole number. Boiling point of water in Kelvin is 373. So notice that the difference in Kelvin is also 100, same as Celsius. So the Kelvin scale and the Celsius scale are very similar in terms of the scaling. The 0 point is just very different. Okay, so that's just something to notice. And we can use this to help us convert between Kelvin and Celsius. There's an equation that can be found on reference table T, and it is Kelvin temperature is equal to the Celsius temperature plus 273. So let's try this. Liquid nitrogen boils at negative 196 degrees Celsius. What is the temperature in Kelvin? So if I start with Kelvin equals Celsius plus 273, and just substitute in the Celsius temperature, Kelvin equals negative 196 plus 273. I bring my calculator back. We can do 196 negative plus 273, and we're going to get Kelvin equals 77 Kelvin. Now, the convention for Kelvin is that we don't put a degree symbol there, but if you do, it's fine. Okay, but you'll typically not see the degree symbol when you see Kelvin temperatures. Volume. Volume is a measure of space occupied by a sample of matter. How do we measure volume? Different scales that you might be used to are liters, that is the metric unit of volume, or typically you might be more familiar with ounces or gallons. We are not going to use those in this class. Okay, we are going to use the metric unit. To convert these units, we are going to go back to the dimensional analysis, and let's change this here. This shouldn't say standard pressures. This should say standard volume. Okay. So we can say that knowing that the equivalent quantity is 1 liter is equal to 1,000 milliliters. And that's what we can use in our conversion fraction. So here we have a liquid having a volume of 48 milliliters. This is our given. And we are solving for liters. So start with your given quantity, 48 milliliters. We're going to cancel milliliters by putting the unit in the denominator. Solving for liters, so we're going to put it in the numerator, knowing that 1 liter is equal to 1,000 milliliters. And now we know, milliliters are going to cancel. Now we know that we're going to divide by 1,000. So 48 divided by 1,000, and you get 0.048 liters. And there you have it. All right, so in this lesson, we have learned how, we've learned the properties of gases, and we have started our explanation to try to understand how that behavior can be explained by thinking about gases in terms of their particles. And we have explored what pressure is, what temperature is, what volume is, and the units that we measure those three quantities in. All right. Okay, everybody. Thank you so much, and we will see you back in the classroom.